All right. Yeah, so let us use a simple example to, look at that whole problem. But the most important part, the optimality of the solution here. Yeah. Problem 23, knight's move problem in chess. Yeah. So I hope, many of you know the chess, are familiar with, playing the chess game. Yeah. All right. Here we have a chessboard, but we only look at the knight. Knight is very special. The move of knight, very special. Find the minimum number of moves needed for a chess knight to go from one corner of a 100 times 100. It is not a standard chessboard. It is a special board, 100 times 100 board, okay, to the diagonally opposite corner, right? Yeah. The knight's move, hope you know how a knight's move, the rule about knight's move, okay? L-shaped jumps, yeah. So that's here, one example. 2 squares horizontally and 1 square vertically. Okay, so that is one way. Another way, 2 squares vertically and 1 square horizontally. Another, yeah, you can move in another way. All right. Yeah, followed by, yeah, so that's a, special case. Yeah, so we move from here, we can move there. Okay, yeah, from there we can move there. Okay, yeah, all right, yeah. Now the question, we want to find the minimum number of moves from one corner to diagonally opposite corner for 100 times 100 board. Because we want to make the problem a little harder. If it's A by A, then you try a few times, you get a solution. But for 100 times 100, it is very hard you try explicitly. Because it is hard to draw that big board, right? So you have to use some deductions. Yeah. You have to explore some rule to solve this problem. Yeah. Here, we use the greedy algorithms. Now, it's a simple problem, so can we use the greedy algorithm to solve it? Yeah. It is an optimization problem. Yeah. So that's what, every time when you see an optimization problem, you can consider greedy algorithm and dynamic programming. Yeah. The easy part for a greedy algorithm, implementation based on intuition. Yeah. When you make decision, local decision, not global decision, then you just get the best you can get. That's why the implementation point of view, it is relatively easy. But there is a hard part. The hard part is prove optimality. How do you know this is the best solution? That part is hard to prove. Yeah. So let's look at this example to see, how to do these two things. First, let us apply the greedy strategy. What is the greedy strategy we use? Yeah. Because there are many different ways to use the greedy strategy. So here we need to find one particular way, that can give us good result. Yeah. Observations. The shortest distance. First, we have an idea how to get the shortest distance between these two knights, right? Shortest distance between two opposite corners is the diagonal. If we draw this diagonal, geometrically, that is the shortest distance. But we have restriction, we have constraint. Yeah. The problem is a knight cannot move along the diagonal in every step. That's the hard part. Yeah. How can you make a knight move along the diagonal? You know? Yeah. L shape, right? We have to follow the L shape move for a knight. Yeah. Yeah. So we cannot. Then we make our strategy. So here we use a principle for greedy strategy. What's that? Make your best local choice at each step. When you have freedom to make choices, here we have many different choices, right? So when you have that, move as close to the diagonal as possible. That's our greedy strategy. Although we cannot precisely move along the diagonal, can we make it the closest possible around diagonal? We can do that. That is our greedy strategy. Okay, yeah. So first we move to this location, very close to diagonal, not exactly on the diagonal, but very close to the diagonal. But next move, it is on the diagonal. Okay, another move, yeah. So here you can see every 2 steps, 1, 2, we get to the diagonal. Another 2 steps, we get to the diagonal. Okay, every 2 steps, we get on the diagonal. Yeah, that's pretty good, right? Yeah. Now the question. How to calculate the total number of steps needed. Yeah. We need to find a rule to do the calculation, to do the counting. Here we are doing the counting step. We count the number of steps. Yeah. How do you find some nice rule you can apply on your counting? Yeah. Counting based on coordinates. Here we need to use the coordinates to give us some idea about the moving rule. Yeah. So what's that? Starting point. When we start, there is a coordinate, this location. Yeah. The first row, first column. So let us use the coordinate number 1, 1. Yeah. Second, yeah, the destination, remember that 100 by 100 board. The destination is 100, 100, XY coordinates. Yeah. Now, the move. Yeah. All right, we do some trials. Yeah. The first time, 1, 1. Yeah. So let's use this example here. This location, what is that location? 3, 2. Then, next time, 4, 4, right? Yeah. Then next time 5, 6. Then 7, 7. Here you can see. Yeah. And the destination 100 to 100. Can we get some nice rule here? Right? Yeah. Excuse me. Ah. All right. 1, 1. It is on the diagonal. All right. Let's look at the next point on the diagonal. 4, 4 on the diagonal. The next point, 7, 7 on the diagonal. All right. The last one, 100, 100, also on the diagonal. Okay. Can we find some common property for all these points? Yeah, that's important to find that rule. Yeah, you can see 3k plus 1 If you divided these number by 3, the remainder is 1. Okay? All right, so 1, 3 times 0 plus 1. 4, 3 times 1 plus 1. 7, 3 times 2 plus 1. Okay? 100, 3 times 33 plus 1. Yeah. So that's the rule we can use here. Okay? Yeah. How many steps do we get at? Okay? For each 3k plus 1 number, we need 2 steps, right? We need 2 steps. Every 2 steps, we get to the next 3k plus 1 number. Okay? All right. So here, the number of moves. The number of moves we have. Okay? Yeah. 2 times 33. Yeah. Or we can think in this way. Okay? Yeah. We define a big jump. Yeah. The small jump is like this. Okay? Big jump, that is the 2-step jump. Okay? How many 2-step jumps we need? Okay? 33 2-step jumps. We need 33 2-step jumps. Okay? Yeah. The first one, 4, 4. Okay? The first one, 3k plus 1. K equals 1 corresponds to the first 2-step jump. The last one, 3 times 33 plus 1. So from 1 to 33, that's 33 2-step jumps. Right? So that means 66 moves. That's the counting number. So we need 66 moves from this corner to that corner on 100 times 100 board. Okay? Yeah. So here we apply the greedy algorithm. We find a solution. Next immediate question. Is this solution optimal? How do you prove it? How do you convince people it is optimal? Right? Yeah. That step relatively hard. Harder than finding a solution. Yeah. But we need to do that. Yeah. If you can, you need to do that. Sometimes it is too hard, so nobody can do it. It's possible. Yeah. All right. Prove optimality. When we prove optimality, usually we need some special tool to do it. Now, we need some very special tool to do it. Yeah. That tool sometimes very smart, very special. So here we have that situation. Yeah. All right. Prove that it is the fastest solution, the fewest number of steps, the fastest solution. That means nobody can use 65 steps to make it. No, the minimum number of steps to make it, 66 steps. Yeah. But the problem is nobody can try all the possibilities. If someone wants to do exhaustive search, impossible. Don't even try it. Yeah. That number is huge number. Yeah. You know, too bad. Yeah. Too stupid. Yeah. All right. Here we use a special tool. That tool is called a Manhattan distance. That is a special tool we need for this example. Very effective. Okay? Yeah. What's the meaning of Manhattan tool? Manhattan distance? Yeah. The sum of the horizontal and the vertical distance between 2 points on the grid. Okay? Because on the grid, if we have to move horizontally, vertically, right? So it is not good to calculate the diagonal distance directly. So another way to calculate distance, horizontal, vertical steps adding together, the Manhattan distance. Yeah, you know, some will create that name. Okay, yeah, so we call it. Yeah. Now, we use this as the tool, as our analysis tool. Let us calculate the Manhattan distance between those two knights for 100 by 100 chessboard. Horizontally, distance 99, right? You move 99 squares. Vertically, also 99 squares. Adding up these two numbers, 198 units of move, units, the distance long. Okay, yeah. How do we use it? After we get this distance number, next, let us look at a knight move. For each step, your knight move toward your destination. Toward destination, that means the distance between the current knight and the destination position is reduced more and more. Every step you reduce the distance, Manhattan distance. You reduce the Manhattan distance, right? But what is the maximum number of Manhattan distance you can reduce for each move? Okay, 3. Horizontally, you can at the most you reduce 2. Vertically, you at the most reduce 1. Or either way, you combine horizontal, vertical, you combine 3. So every step you can reduce the Manhattan distance by 3. How many steps? You do division. So the minimum number of steps you need, 198 divided by 3. That is 66. Yeah. This way, it gives us the best solution. Because otherwise, if you do not use 66, you have no way to get Manhattan distance 198. So that's why this is the best solution. Okay, so we proved the optimality of our solution. Yeah. So you can see it is not that hard, but to solve this problem completely, you need to do a lot of work. Here, you need to use a special tool, Manhattan distance. If you do not know this tool, or you do not realize this special tool, it is very hard to solve it, especially on that optimality issue. Yeah. All right, so we finish B.1.